In this video, we're going to talk about significance tests about means. Remember when we were doing this, when we were talking about proportions, we call these significance tests hypothesis tests, right? So significance tests and hypothesis tests are exactly the same thing, right? We're basically going to follow the same 5 steps that we followed when we were dealing with not confidence interval, but hypothesis tests for proportions, but we have to adjust it because we're going to be dealing with different variables. And with different variables, we have to handle them differently when we do statistics with them, all right? But first, what we're going to do when we're conducting a hypothesis test for a mean is to check the assumptions. Remember, we check assumptions because we need these things in order for our methods to work appropriately. If any of these things are not satisfied, it could cause our results to not be believable. And so one of the first assumptions, which is also actually an assumption that we should have stated when we were dealing with the confidence intervals for a population mean, but we want to ensure that our variable is quantitative. And remember that quantitative is the same thing as saying numerical, right? And so when we're dealing with proportions, we had categorical variables where our variables, the variable that's measured on the individual level takes on one of several categories, versus here when we're dealing with quantitative variables, our variables are numerical. Not only should our variable be quantitative, but the data should be obtained using randomization. And this kind of allows us to say that our sample is representative of our population. It's good for inferences if we use that randomization. Okay. Also, when we think about sampling distributions, the sampling distribution repeatedly samples random samples, right? And so since we use our sampling distribution, we need that randomization as well. The third and last assumption is that the population distribution is approximately normal. Remember, normal is basically the same thing as saying bell-shaped, okay? Now, our central limit theorem applies to when we have quantitative variables. And so if the population distribution is not approximately normal, then with a large sample size, and so if we have a large sample size, and we say large is n is greater than or equal to 30, by CLT, we know that our sampling distribution of the sample mean is bell-shaped. Okay? And so we can still use these methods to help us come up with or to conduct our hypothesis tests. All right. Now, if our population distribution is not normal, right, and our sample size is small, okay, small is less than 30, then we have some problems, okay? We have some problems. Our assumption is not satisfied. All right. And this is very crucial when we have small sample size and our alternative hypothesis is one-sided. We can check our normality assumption that the population distribution is normal by checking the graphical display of the data that we collect in our sample. Remember, your sample, especially if you use randomization, should be representative of your population. So if you look at the graphical display, remember we have a quantitative variable, so we can use a histogram, a stem and leaf plot, a dot plot, so on and so forth, to get a view or a graphical display of what our data looks like from our sample. If that looks normal, and our sample is our best guess of what's happening in the population, then we can kind of infer that our population distribution is normal as well, okay? And so one of the things that you want to get in the habit of doing is when you conduct a hypothesis test for a mean, look at a graphical display and see if it's approximately normal. If it's approximately normal, then you're going to say that your population distribution is probably approximately normal. If it's not approximately normal and your sample size is small, you may have some issues, but we're going to get there in just a second. One of the things you also want to check with your graphical display is you want to check for extreme outliers. So what outliers do is they skew your data. And so remember, when we have a skewed data set, for instance, something like this, right? Then what it does is where our median will be over in this area here, our mean gets pulled into the direction of the actual tail of the distribution. And so when we want to say what is the center of our data, well, the center of our data is not necessarily our mean anymore, it's basically our median. And so the median should be used rather than the mean, right? And so extreme outliers may pose some issues whenever we try to make inferences about a population mean, because the mean itself may not be a valid measure of the center of your data. All right. So I'm always going to check that the population distribution is normal. If it is not normal, we can use the central limit theorem that says if my sample size is greater than or equal to 30, then my sampling distribution is normal. So we can follow the steps that follow in this process of conducting a hypothesis test. Our issue comes in when we have outliers, because it may mean that the mean is not even an acceptable measure that's representative of the population anyway. All right. Now, I said all of that stuff about normality and all that stuff like that. I do want to talk about a new concept that we hadn't discussed before. The t distribution, which is that t statistic, which is a bell-shaped curve centered and symmetric about 0 that has thicker tails than a normal distribution. That distribution is a robust distribution in terms of the normality assumption. All right. So any method that uses the t distribution is robust. That means even though this normality assumption may not be satisfied, the method still works. And so what happens is statisticians, they come and well, they don't come. They go through a process of studying different scenarios on which a certain method works and when they don't work, when they fail to work, basically. And so what they found is that even when the population distribution or even the sample distribution is not normal, this method that we're going to use that uses the t distribution still works appropriately. It's still valid, even though that normality assumption does not work. And it's because that t distribution allows for a little bit more variability than the z distribution. All right. And so although we may not have normality, it's robust to the normality assumption. So if that fails, we still can believe our results. All right. So that's what that means. So a method is robust. So this method is a robust method to normality violations. So if it doesn't satisfy the normality assumption, it violates it. All right. So we're going to go to step 2. We're going to state our hypotheses. Of course, just as with the hypothesis test for your population proportion, we have a null hypothesis for our population mean. Quantitative variable, we usually use means. All right. And it always does that our population parameter is equal to a null hypothesized value, which we denote with mu sub 0 or mu naught. All right, kind of like when we had our population proportion, we said that the null hypothesis was p equals p sub 0 or p naught. Okay, our alternative hypothesis can take on one of the following forms: is that our population parameter is greater than some null hypothesized value, or it could be that it's less than some null hypothesized value, or it can be two-sided and that it is not equal to some null hypothesized value. Once we get our alternative hypothesis and our null hypotheses, we're ready to proceed with the test. And the session goes to the test statistic, which is step 3. Remember, the test statistic measures how far the sample statistic, and since we're dealing with the quantitative variable here, it's going to be the sample mean, falls from the null hypothesized value which is mu sub 0 or mu naught, based on what we expect if the null hypothesis were true. Remember, this is a proof by contradiction, right? So we assume that the null hypothesis, the population parameter equals some value. We gather our sample through randomization. We make sure that we satisfy all the assumptions, and we calculate this test statistic here. If this test statistic shows evidence against the null, then we're going to reject. If it doesn't show evidence against the null, we don't have enough evidence to reject. All right. And to gather that evidence, this test statistic helps us do that. And it depends on that null, believing that null hypothesized value is actually the true value of the population parameter. All right. The t statistic is very similar to a z statistic. Remember from before, z is always your x. In our case, is going to be x bar because we're talking about a sample mean minus the population parameter, which is mu sub 0, divided by the standard error, and the standard error or the standard deviation, in this case, the standard deviation of the distribution of sample means is sigma over the square root of n. All right. So this is a z statistic. This is used if sigma is known. Remember, your sigma is your population standard deviation. All right. In most cases, that is not the truth. We don't know sigma, and so we use t. All right. And so this is going to be predominantly the test statistic we're going to look at when we're talking about hypothesis tests for sample means or for your population mean, right? It's still going to be that same formula, x bar minus the null hypothesized value of your population parameter, which is your population mean. But instead of having sigma here, like we have with the z, it's going to be s over the square root of n. Okay. And remember, this is your standard error. This is an approximation for your standard error because this is from your sample. This is the actual value of your standard error. This is the estimate from your sample. Okay. And so this measures the distance your sample mean, right, is from your population and your hypothesized population value in standard error units. That's why we divide by the standard error. And this is an approximation of the standard error. Once we get that t statistic, we can go to that t distribution, basically. It looks something like that. And whatever our t is, we can get our p-value. All right. And so it may be on this side of our distribution, or t may be on this side of our distribution, or t may be or include both of these areas under this distribution, right? And so remember, your p-value describes how unusual, unlikely, unusual the sample data would be if the null hypothesis were true, right? And so this is going to be a probability. This is a probability. All right. It summarizes the evidence from the sample, which is the probability of obtaining the test statistic, or one more extreme if the null hypothesis was true. And so we calculate this probability going again to this t curve, this bell-shaped curve, and we attach it to whichever, and we know which tail end to use on this curve by looking at the alternative hypothesis. For instance, if our alternative hypothesis is that the population parameter is greater than the hypothesized value, we use a right tail probability, and we basically find a probability that t is greater than our obtained test statistic. Or if it's less than, we're going to say t is less than, so we're going to get the left tail probability. And if it's not equal to, we get the two-tail probability, and I'm just going to write that as 2 times the probability that t is greater than t star. Okay? And so once we get that, we actually state our conclusion, right? And so we summarize the test by reporting and interpreting the p-value. The smaller the p-value, the smaller the probability, the stronger the evidence against the null hypothesis is. And to see how small we need to be, We think about our error probability, which is also our significance level, alpha. Alpha is our significance level, which is 1 minus our confidence level. And remember, when we're 90% confidence, that means alpha equals 0.10. When 95% confidence, alpha equals 0.05, and it equals 0.01 if we want to be 99% confident, right? And the way we ensure that we know we reject or fail to reject our null hypothesis correctly is that if our p-value is smaller than that alpha, we reject, and we say with p-value equal to whatever p-value we get in practice, so we'll fill this in with the number that we get for our p-value, we have sufficient evidence that our alternative hypothesis is the way we want to go. Or if our p-value is greater than alpha, we do not reject, or we fail to reject the null hypothesis, and we say we do not have sufficient evidence that the alternative hypothesis is true. Okay? And that wraps up the 5 steps to our hypothesis test. So let's look at an example. It is said that when students enter college, they usually gain 15 pounds over their first academic year. This is known as the freshman 15. Although this is the case, a researcher at a Southern university believes that students at his university generally do not gain any weight their freshman year. A random sample of 67 freshmen at the researcher's university were weighed at the beginning of the academic year in September and at the end of the academic year, which is in April. Then the difference in weight from those two measurements were calculated. So they took the April weight and they subtracted from that the September weight. And so if you get a positive value, that meant the person weighed more in April. That means they gained weight. And if you get a negative value, since you're doing April weight minus September, that means the September weight was larger. That means that they lost weight. So negatives means they lost weight. Positive means they gained weight. Okay. A graphical display and summary statistics of the results are below. We want to find out, is there evidence that freshmen at the university gain weight? Use a significance level of 0.01. Okay. And so even before I get to the summary statistics, all that stuff like that, one of the things we can do is we can check the assumptions, right? So I'm going to go to step 1 and I'm going to check assumptions. Well, 1, our variable is difference in weight. Difference in weight is numerical, right? Right? That's quantitative. And so we satisfy that first assumption that our variable must be quantitative. The second assumption is randomization. If I read the problem carefully, it says that they found a random sample of size 67. So we do have randomization. So that's satisfied. That third and final assumption is that our population distribution is normally distributed, right? There is nothing that talks about the distribution of the sample, of the population. That's what we're worried about here, right? But we do have this graphical display here. So we don't have any information about the population, but we do have our sample. This is from the data that we collected. Notice that it does look a little bell-shaped, right? I can see myself drawing a bell-shaped curve. It might go higher than that, I'm sure. But then on this end of my distribution, it kind of has a longer tail than that one there, all right? Even though that's the case, this is a pretty normally distributed population or sample distribution, right? However, these may be outliers. Right? And so we may have some potential outliers in our data that we may have to get through. But what we're going to do is we're going to continue with the analysis. Even if you don't believe that this is normally distributed and that because this is a larger tail on this side, note that the sample size is 67, which means that our central limit theorem which states that if we have a large sample size, then the sampling distribution of the sample mean is normally distributed, which means we have a bell-shaped distribution for our sampling distribution, right? And so even if this shape isn't bell-shaped, which I believe it is, then this n equals 67 allows us to proceed using our t distribution for inferences in the next step where we calculate our test statistics. So the t distribution seems okay. These may or may not be outliers. There are checks for that, but we're going to proceed, right? So we're going to say that normality is okay due to the large sample size, but there are potential outliers. So results are tentative. And so what is usually done in practice, people usually take out the outliers, rerun the analysis, and if the results are quite similar, then they'll put them back in and say that, oh, okay, although I thought those were outliers and it would really change my results, I'm going to keep them back in there because they're not changing my results at all. If you put the outliers in there, you take them out and you do the analysis and your results are quite different. Some people choose to report both. Some people go in and try to explain why there may be outliers and explain it that way. But there are ways around it in practice. It's one of those things that when you get into the field, your field usually uses a guideline to kind of help you out with that. Okay. But always check for those outliers. All right, so we're going to proceed with the next step. I just wanted to make a mention of that. Let's go to step 2 where we talk about our hypotheses. Our null hypothesis is that mu equals something. Our alternative hypothesis is that mu is going to be greater than, equal to, or less than or equal to something, right? So what we want to do is see, is there evidence that the freshmen at that university gain weight? Well, gain weight means that the difference is going to be positive, right? And so my alternative hypothesis is going to be greater than 0. The difference in weight from April to, for September to April should be greater than 0 if they gained weight. And our alternative hypothesis needs to include that value. So our null hypothesis needs to include that value. So it's H0 mu equals 0. Once we have our hypotheses, we're going to go ahead and get our test statistic. Our test statistic here is going to be either a Z or a T. All right. If we know our population standard deviation, we're going to use a Z. If we don't know our population standard deviation, sigma, we're going to use a T distribution. No, there's no mention of any distribution, any population parameter in this write-up here. But we do know our sample mean here, X bar, our sample standard deviation here, and our standard error, that's S divided by the square root of N. And then, of course, we have our N. So we don't have population values, we have sample values. That means we're going to use a T statistic because we don't know sigma. And so our T statistic is going to equal X bar minus the null hypothesized value all over S divided by the square root of N. All right, I'm going to zoom out a little bit. Not that much. Our X bar was that I'm going to round to 4 decimal places, 2.5988. My null hypothesized value is 0, and I'm going to divide that by my standard deviation over the square root of 67, which is also given in that chart as that 1.04698814. And so I'm going to get my calculator and I'm going to put those values in. And I get approximately 2.4 8, 2, and then I'm going to round it to 4 decimal places, 2. Okay, and so this is my test statistic. Now we can go to step 4. Notice here also, if you were to write this as S divided by the square root of N, remember you have S here and you have N here, right? But since I have S and N and they give me the standard error, I know it's going to equal that value right there, all right? So I didn't do that calculation there because it was given to me in the table, all right? Now we're going to go find the p-value, right? The p-value is going to equal the probability that my t from my table is going to be greater than, because this is my alternative hypothesis, so I'm going to use that same inequality, the t value that I got. Okay, now if I go to my t table, which is here, notice these are all values of t. These inside this table, unlike the z table, these are t values. These are values of t. Well, in my write-up, I already know what value of t I have. T equals 2.4822. So how am I going to get the probability if this table only gives me t values? All right. In this case, we're going to have to use technology. And so for your homework and all that stuff like that, I want you to go to StatCrunch. And so I'm going to go to StatCrunch and I'll show you how we can find the t values. When you open up StatCrunch, okay, this doesn't want to open up. That's why. All right, I'm going to go to Stat. I'm going to go to Calculators, and I'm going to get to my t distribution on this Calculators menu. Go to T. All right, so what I have here is a t distribution. It looks like our normal distribution because it is bell-shaped, but it is a t distribution, and the reason I know that is because it has degrees of freedom. Remember, your degrees of freedom is your sample size minus 1. If I go back to the problem we were dealing with, our sample size was 67. So instead of having it as 67, 67 minus 1 is our degrees of freedom. Okay? Now, we know our t value. We have from our work here that t has to be greater than 2.4822. So when I go here, I know it has an X there, but it represents a t. Instead of less than, I'm going to have greater than, and I'm going to do that 2.4822. If I click compute, I'm going to see that I get a p-value or a result of 0.0078. 0.0078. And so my p-value in this example equals 0.0078. All right, that's my p-value. And so number 5 is to make our decision, right? So my alpha is my significance level. All right, it says for us to use a significance level of 0.01. So alpha here is 0.01. Our p-value is 0.0078. Notice my p-value is less than my alpha. When that is the case, it's less than or equal to, I reject H naught, okay? So H naught was that my mu equals 0. So I'm saying that that is not true. And my only other alternative is that it's going to be greater, right? And so I'm going to say with p-value equal to 0.0078, we have sufficient evidence that, and I'm going to state my alternative hypothesis, mu is greater than 0. That means students generally gain weight their freshman year. Now, we don't know how much weight they gain. That's what a confidence interval is for. But we just tested that hypothesis that of whether or not they gain weight, right? Students at that university gain weight. Freshman students at that university gain weight. And that is how we conduct a hypothesis test for a mean. Now if we want to check ourselves, we can go back to StatCrunch. If I want to check myself, I can go to Stat, T-stats, because we use a T statistic. We only have one sample here. We'll get to two samples later. Now I'm going to say with summary. All right. The sample mean in that example that we just looked at was 2.5988. Our standard deviation was 8.5699. I'll put that 19 in there. And our sample size was 67. Notice our null hypothesis was 0 and our alternative hypothesis was greater than. Mu is greater than 0. All right, I'm going to go to compute, and it's going to give me results of that test. It's going to give me my sample mean, my standard error again, my degrees of freedom, my test statistic, which is that 2.4822. We round it to the 4 decimal places. And it also gives us that p-value of 0.0078. And so that's how you can use StatCrunch to check your work. And that ends this video. We'll get to the other two examples when I return.